Is Earth being watched by something not of this world?
Oh my gosh, what is that? What is that?
It's pointing in the wrong direction entirely. When NASA's Juno spacecraft turned its instruments toward the Interstellar Visitor 3I Atlas during its extended mission observations, it captured images of tail structures that, according to our understanding of comet physics, simply should not exist. This discovery has sent shockwaves through the space physics community. A leading scientist from Harvard University is suggesting that what Juno observed isn't cometary dust at all. We might be looking at the first confirmed propulsion system from beyond our solar system. The probe's findings have opened a universe of terrifying and exciting new possibilities about what's actually generating the directed emissions trailing behind this visitor. A revelation from Jupiter's orbit. In the vast emptiness between worlds, where NASA's Juno probe continues its extended mission around Jupiter, something extraordinary emerged from the spacecraft's observational data of humanity's third confirmed interstellar visitor. When Juno's instruments first detected 3I Atlas approaching Jupiter's gravitational sphere in early 2026, mission planners expected to observe typical cometary behavior, random dust emission creating chaotic tail structures blown away from the sun by solar radiation pressure. What Juno's cameras and spectrometers revealed was something entirely different. The spacecraft's unique vantage point from Jupiter orbit provided perspectives of 3I Atlas that Earth-based telescopes simply couldn't achieve, revealing tail structures that challenged every known model of natural comet behavior. At first, the tail appeared unusual, but potentially explainable. Multiple ground-based telescopes had already detected odd characteristics in 3I Atlas's emission patterns, but as Juno's data was analyzed, the routine became revolutionary. The probe wasn't just observing comet dust. It was documenting structured emissions that looked suspiciously like controlled thrust. You see, when comets develop tails, physics dictates that dust and the tail structures weren't just unusual in appearance, they were exhibiting characteristics identical to spacecraft propulsion systems. The thing nobody tells you is that natural comet tails don't demonstrate the organized, directional characteristics that Juno observed. What the probe detected looked less like random dust emission and more like controlled thrust vectoring from an engineered propulsion system. This wasn't cometary outgassing. This was something that appeared to be actively maneuvering. What Juno's instruments actually detected. Many people are crazy about space propulsion, but the scientific community is obsessed with tail physics that shouldn't be possible. As Juno continued its observations of 3I Atlas through its approach and departure from Jupiter's vicinity, the spacecraft revealed emission characteristics that defied every known model of natural comet behavior. The breakthrough came when Juno's Jovian infrared auroral mapper analyzed the spectral signatures of the tail emissions. Instead of the broad-spectrum thermal radiation typical of heated dust particles, the probe detected narrow-band emissions at specific wavelengths that suggested controlled chemical reactions rather than random sublimation processes. When Juno's microwave radiometer measured the thermal properties of the tail, it found something that left the propulsion physics community speechless. The emission pattern showed organized thermal gradients that indicated directed energy release rather than the chaotic heating expected from solar radiation interaction with comet dust. The thing is, Juno's unique orbital position allowed it to observe the tail from angles impossible for Earth-based telescopes. From these perspectives, the probe detected that the emissions weren't being blown randomly away from 3I Atlas. They were being directed in specific vectors that changed in coordination with the object's trajectory adjustments. Dr. Bryce Bolin, who analyzed the ground-based observations, had noted that the tail is going in a strange direction, but Juno's data revealed something far more systematic. The tail wasn't just pointing in the wrong. Juno's energetic particle detector found that the tail emissions contained organized particle streams with velocity distributions that matched theoretical models of controlled plasma propulsion. These weren't the random particle velocities expected from thermal sublimation. These were precisely controlled emissions consistent with ion drive technology. You see, advanced spacecraft propulsion systems create particle streams with specific velocity profiles designed to maximize thrust efficiency. Natural comet outgassing produces chaotic particle distributions with random velocities determined by thermal energy. Juno detected the former when it should have observed the latter. The first major evidence of controlled propulsion came when Juno observed the tail emissions responding to gravitational perturbations from Jupiter. Instead of behaving like passive dust clouds affected by gravitational forces, the emissions adjusted their trajectories to compensate for orbital mechanics, behavior that requires active thrust control. Dr. Marco Micheli from ESA, who had been tracking 3I Atlas's orbital mechanics, found that the tail emissions were providing precisely the thrust vectors needed to maintain the object's calculated trajectory. The emissions weren't random byproducts, they were controlled thrust, providing navigation corrections. The thing nobody tells you is that maintaining such precise thrust control requires computational guidance systems operating faster than human mission planning capabilities. Juno observed thrust vectoring adjustments occurring in real time, response to gravitational perturbations with millisecond precision. Furthermore, Juno detected that the tail emissions would adjust intensity and direction when observed by different spacecraft across the solar system. The probe documented propulsion system modifications that seemed designed to optimize thrust while maintaining observability, suggesting awareness of multiple observer positions throughout the solar system. The systematic propulsion operations, when objects from deep space develop tails during solar system passage, the probe observed systematic changes in the object's gravitational signature that matched theoretical models of spacecraft consuming reaction mass for propulsion. Dr. Avi Loeb from Harvard, who had proposed using Juno to study 3I Atlas, made a statement that would echo through the space physics community. When presented with Juno's propulsion analysis, he stated that the spacecraft had documented systematic thrust operations indistinguishable from advanced spacecraft propulsion technology. The propulsion operations became even more systematic when Juno observed coordination between tail emissions and the object's rotation period. The probe detected that thrust vectors would adjust based on the object's orientation, suggesting three-axis stabilization and attitude control systems operating in coordination with propulsion management. Dr. Adam Hibbard, who had calculated Juno's intercept trajectory, found that 3I Atlas demonstrated propulsion efficiency that exceeded current human spacecraft technology. The thrust-to-mass ratios and specific impulse values detected by Juno suggested propulsion systems operating at theoretical performance limits. The conclusion was inescapable. 3I Atlas wasn't just producing unusual tail emissions. It was operating controlled propulsion systems with the efficiency and precision of advanced spacecraft technology, managing thrust vectors, fuel consumption, and attitude control to achieve navigation objectives that natural processes couldn't accomplish. But not all things are what they seem. Science demands that we explore every natural possibility before accepting extraordinary conclusions. The systematic propulsion behavior detected by Juno could have explanations that push the boundaries of known physics without invoking artificial thrust systems. The organized emission patterns could result from previously unknown internal chemical processes that create the appearance of controlled propulsion through complex subsurface reactions. The precise thrust vectoring might be explained by exotic electromagnetic interactions with Jupiter's magnetic field. Perhaps the most unsettling possibility is that the propulsion behavior detected by Juno represents natural phenomena operating according to principles so advanced that they challenge our understanding of what's possible in space physics. What if 3I Atlas represents natural processes that have evolved propulsion capabilities over billions of years of interstellar travel? This brings us to the most profound question raised by Juno's observations. When a spacecraft designed to study natural phenomena detects systematic propulsion operations that exceed the capabilities of human space technology, are we witnessing impossible natural processes or the first confirmed observation of artificial propulsion systems operating in our solar system? The verdict from Jupiter orbit. When you analyze the complete observational data from Juno's extended mission observations of 3I Atlas, the spacecraft emerges as having documented propulsion operations that defy natural emission physics. The systematic thrust vectoring, controlled particle streams, and coordinated navigation corrections paint a picture of advanced spacecraft technology rather than natural comet tail formation. Juno's data reveals propulsion systems that maintain coordination they shouldn't be able to maintain, produce thrust at efficiencies natural processes can't achieve, and demonstrate operational precision that exceeds known natural phenomena. Whether this represents exotic natural propulsion physics or something that transcends natural explanations entirely, Juno's observations have documented propulsion technology unprecedented in the history of space exploration. Dr. Scott Bolton, when presented with the complete Juno propulsion analysis, stated that the observations had moved 3I Atlas into the category of objects requiring extraordinary explanations. The evidence from Jupiter orbit consistently points toward propulsion operations that exist outside the known parameters of natural emission processes. When you look at it that way, the systematic propulsion behavior detected by our most advanced planetary probe is telling us those propulsion operations look exactly like spacecraft technology. Let us know what you think in the comments.